Here we go. So this first one here, you've got the 2,000 newtons per meter, and then you've got 12,000 in the middle, and then the couple here at 20,000. All right, you need to find their reactions. And they're 12,000 over here. And then I think it's 4,000 here. All right. So you're going to kick up to 12,000. You're going to drop by this area, which is negative 4,000. It's 20,000 times 2. So that'll get you down to 8,000. Then nothing happens. You'll hit the 12,000. That will drop you by 12,000. You'll get down to negative 4,000. And then you'll finish that off there. Then you'll want to find the areas. This area here is 10,000 by 2, so it's 20,000. This area here is 8,000 by 2, which is 16,000. Then you've got that couple in there, so you're going to want to find these areas independently. To the left of the couple is negative 8,000, and to the right of the couple is negative 8,000. So the shape on this thing will be kind of like this. You'll curve up with a decreasing slope because these values are decreasing. That'll get you up to the area, which is 20,000. You'll keep going up another 16,000, so that'll get you up to 36,000. That'll be a straight line because that's a block. There's no change in shear there. Then you'll drop by 8,000 to 28,000. Then you hit that positive couple of 20,000. That'll drop you immediately down by 20,000, so you'll be at 8,000. And then you'll close off to 0. So there's the shear in the moment for that. We good with that? All right. All right. This one here, people seem to do pretty well at it. You know, you want to find the shear and moment diagram. The moment peaks out at 4320. Find BH cubed over 12 for I. It's 0.00035. And then just plug in my over I for each one of those locations. The only thing that changes there is the y, the distance from the neutral axis to the points. Okay, we good with that?
Can you go back and explain that shear diagram?
Okay, the shear diagram goes from 0 up to the reaction at 2,880. Then it'll drop by an amount equal to the area under that loading diagram, which is negative 5760. So it drops from 2880 down by 5760, so that gets you down to negative 2880. And then the reaction takes it back up to 0.
And then how do we find the 0 point again?
The 0 point, well, in this case, it'd be in the middle because you start at 2880 and drop to a negative 2880.
Okay.
But then also you could find it kind of via slope because you've got a slope here of 960. So what you're going to do, you're at 2880. And you want to know how far you've got to drop at 960 times x so that you equal 0. Solve for x and it'll be 3, I think. Yeah, 3. Okay. So that's how you do that. Yeah. Other questions on that? Okay, the next one we went over pretty well. The thing on that is that moment diagram jumps from positive to negative, so you have to account for that. So it's positive at C, positive at B, negative at C. Okay. So you just go through, find y bar for that T-beam, it's 5.4. Find the moment of inertia, it's 157.2. And then find where the couples are. Okay. So the couples off the moment diagram are 216, or excuse me, the moment off the moment diagram is 216,000 at B, 288,000 at C. So you plug those values in. I just found the compression and tension at B and at C. What's on the top and the bottom depends on what's happening here. See, the beam will go into that shape. So the compression is on the inside of the curve, and the tension is on the outside of the curve, basically. So that's what's happening there with that, and you'll see that reflected in the moment diagram. Okay. On that one. So then what that influences is the C values, because C is 5.4 to the bottom, or the out there, which is where the, on the first one, the tension's on the bottom, but on the second one, the compression is on the bottom. So you kind of have to work those numbers, the MC over I, putting in the C value that's appropriate for where the compression or tension are at. Okay. Okay, the shear problems here. You want to find that shear diagram, solve for the shear in the location you're interested in, point B in this case. So at B, the shear on this one is 1200. Then you're using that VQ over I formula. Now what I is the area that would shear off. So for instance, for here, the area would be the yellow. 0.04, which is the thickness, times 0.02, 0.0008. Then you would look at the distance from the neutral axis to the centroid of that area, which would be the 2 centimeters up plus half of 2 to get to the centroid of that area. So it's 0.03 meters. Okay. Once you've got the Q's for each one of those locations, you just plug in VQ over IT and solve for the shear, okay, at the different locations. All right, so that's just some of the homework. Are there any questions on when I hand it back? Okay. All right. All right, so why don't we have a look at this review problem then. Now, for those of you online, there's a review problem in Moodle right there. It's the shear and bending stress review problem. It's here. The key is right below in Moodle, so there they are, okay? And then we're just going through this thing. So let's have a look. And let's kind of get our way through this today if we can. If not, we'll try and finish it tomorrow. All right, so the first thing to do is to find the reactions on the beam. And if you haven't done that, so there's the beam. And then we just want to find the reactions on that. So if you're online, maybe pause and go through that, then we'll look at them real quick. Okay, so see if you can work through those. Okay, now after you find the reactions, the thing to do after that is to find the shear and moment diagrams. So that would be the next thing to do. Does everybody have a copy of this? Okay, so why don't we go through the reactions here? Okay, so hopefully if you're online you had a chance to work those out. There we go. So we got some of MA is the 6,000 newtons, and actually I've got a little typo there. That should be newtons per meter, shouldn't it? I think. There we go. Times the distance over which it acts, which is 8 meters. And then you're going to apply that force at the centroid, which is 4 meters over here from here. So that would be 4 meters. As with this, okay? So you're going to take that 6,000 newtons per meter times 8 meters times the centroidal distance, which is 4, and then add in the couple, and then plus 8 RD. So RD comes out to be 12,000 Doing the same thing from D, I get RA is 36,000. What I can then do is check that, because I'll add these two together and get 48,000 when I add them together. And that equals the downward load, the 6,000 times the 8 meters. All right. So that all works out. I've got to check on that, and that's good. Okay. So we're good with the reactions. Okay. Next thing there is to find a shear diagram. So why don't we spend a couple minutes on that. Remember, the couple has no direct effect on the shear. Now the couple affects the reactions, which indirectly affects the shear, but the couple has no direct effect on the shear. Okay? So why don't we run through that. So then once you got the shear, find the moment diagram. Remember, you are going to have to, you're going to have that big jump in the moment diagram when you get to the, to that couple at C. So you're going to have to accommodate that or get ready for that. Okay, so your shear diagram is going to jump up by that left-hand reaction at A, and then it'll come on down as a function of the area of the diagram. Okay. So I'll pause the recording for those of you online. You can just draw a shear and moment diagram, see how you do with that, then have a look at what we're doing. Some of you should pause your recording too and work on that stuff. So there's a shear diagram. Kind of just a straight up and then sloping down. It's skewed. It's kind of pushed off to the right, I guess you might say, because the reactions are out of balance. Y'all okay with that? It zeroes out at 6, I think. Okay. Okay. Now, a couple of things to get off of this. You know, we know we're starting at the left reaction, and we know we're coming over here to the right reaction. It's a straight line in between. If you do and keep in mind that the slope of the shear is the value of the distributed load. So what you're doing there, you're taking 36,000 minus whatever that unknown distance is times that negative 6,000 slope there. So you can say that, set that equal to x and set that equal to 0 then. So you're going to get 6,000x is 36,000. So that's how you find that x is 6. Okay, that's where it zeroes out. Okay, and you're also going to want to know what the value of shear is right there, because the question is one of the questions anyway is to find the value of shear at point B1, I think I call it. That's point B right there. So it's quite similar in form to what we're doing here, because we know we're starting at 36,000, then we're dropping by that slope of 6,000. And you're 2 meters over, I think, on that one, so that should be a pretty quick way to figure that one out, I think, to get that value at B, the shear at B. Okay. So we good with 24,000 at B? We're just at 36,000. We're dropping 6,000 per meter. We're going 2 meters over, so we're down to 24,000 by the time we get to B. So we're good with that?
How is it the 6 again?
What's that?
How is it 6?
Where it zeroes out?
For the left? Oh, where it zeroes out?
Yeah, that's where it's, because I want that because it's the base of the triangle. It's kind of transitioning from positive area to negative area there. That's why I solve for 6. Okay. So got the basic shape of the shear and then the particular values that the shear at point B is 24,000. Because I'm at 36,000, I'm dropping by the slope, which is the value of the loading diagram there. So I'm dropping by 6,000 newtons per meter over 2 meters. So I'm down to 24,000 at B. So that's going to be the value I'll use to find the shear at B. That's V, is what that is. Any question?
Are you turning this in?
I don't know if we'll turn it in. I just want you to be able to work through it because. Don't worry about that. Even if I don't think we'll turn this in. We'll just go through it just so we're good, ready for the final. Because this is a lot of stuff that'll be on the final. Okay. So we're doing all right. Okay. All right, and then that zeroes out at 6. Okay, so we get to the moment diagram. You all get into that? It ought to be kind of a parabolic moment diagram with this big shift in it, right where that concentrated moment's at. So that'll just drop the parabola down. If you were to take that out, it would be a smooth parabola, but you got that big jump in it is kind of what's going on. Okay, you okay with that? So I got a moment diagram like that. It goes from 0 up to 108,000. The slope starts very positive, so that's a positive slope up there because the slope on the moment is the value of the shear, and then the slope reaches 0. So that's kind of the natural maximum. Even if that jump wasn't in there, that would be the maximum in this case. Not often the case generally, but that is on this one. And then what happens is that whole parabola just gets slid down by 96,000, okay? Now that's a positive 96,000 moment in there, but what the beam's gonna do is react to that. The beam internally will come back the other way to balance that out. That's why this goes in the negative direction for the change in moment. So you do have to remember that a couple will cause a change in moment with the opposite sign of how the applied couple, of the sign of the applied couple. All right. So we good on that? Okay. So that's the moment diagram. And I'm getting the area of that triangle there is 108,000. So it goes from 0 to 108,000. We're going to drop by 96,000. So we end up at 12,000, which is and that area for the second triangle is negative 12,000. So that's all good. That checks out. Okay. These things should balance and start and end at 0 in these diagrams. So what you've got now is you've got the stuff you need. You need the shear at B, okay, 24,000. You've also got the maximum moment, 108,000. That's the information you get off these diagrams. Right, now the other stuff you need are kind of shape type properties based on the cross section of the beam. So that's the next thing to look at. So the next thing to do, if we're good with this, is to find the centroid. You know, where's the centroid of this thing? What is y bar for that? That's the next thing to figure out, okay? So what I would do, I would break it up into two pieces. You have this little bit of a jog in here, not much, but a little bit. So break the thing up into two pieces. I call them 1 and 2. Find the areas. And then find the distances from the base to the centroids of the areas. That way you can find where the centroid is at for that thing. Because you need that. You need it for two reasons. You need it because you're going to use it to get C for the moment equations. And also you calculate the moment of inertia about that point, that level, that whatever you want to call it. That's where the neutral axis is. How's that?
Yep.
Yeah.
Okay, so you want those two areas, you want to multiply them by their centroidal distances, add those two things together, then divide by the total area. That's how you find y bar. So that's the next thing to do.
That 18 is just the part above the jog, right?
Yeah, that's above that, yeah.
Okay.
So it's, yeah, I didn't give you the total overall. Overall is 22, I think. Yeah. Can't remember what it is. 10.8 is the centroid? No. Yeah, 10.8. There we go. So that top area is 0.0144. The distance to its centroid is 4 centimeters plus half of the 18. So 4 plus 9 is 13. So I've got everything in meters here. Multiply them together, and then the lower piece, 4 by 9, is 0.0036. Centroidal distance is half of 4, it's 0.02. Multiply those together, you get 0.000072. Add everything up, the y bar A and the A, and divide them out, you get 0.108 meters, which is 10.8 centimeters. Okay. All right, so that's where y bar's at. Okay. So now you want to calculate the moment of inertia about that point, at least I think. What do we do here? Yeah, so after you've got that, find the moment of inertia of that shape about that location. That location, what it is the neutral axis. Okay. Okay, so for this you want BH cubed over 12 for each one of the two pieces, plus AD squared. A is just the area, we've got that. D is the distance from the neutral axis at 10.8 to the centroids of the areas. Okay, and you square the distance. Y'all doing okay on that moment of inertia? I just went times 10 to the minus 6. I got 74.2. Is that right? Now the thing on this stuff is, each step is straightforward enough. I get there's something about it, maybe putting all the steps together, but I just look at that formula and I don't, like if I'm going to do bending stress, it's MC over I. I get a moment diagram, I find M. I don't think of anything else. Then I do the centroid and I'll find C. And then I'll do the moment of inertia calculation, obviously, and find I. That's how I work through that, okay? I don't overdo it. I just take it one step at a time. We okay on I there? Are we doing all right? So what I'm doing there, I've got BH cubed over 12 for each of the pieces, the top one and the bottom one. Then I've got the area, the offset distance, and the area times the offset distance squared. And I just add the two together. So you're going to take AD squared right there and add it to BH cubed over 12. Right there. AD squared right here. BH cubed over 12 right there. Okay, and add them up, get the total. And then once I've got the total, I add up the totals. And I get that number. That's the total moment of inertia of that shape about its neutral axis. So, got any questions on that bit? And I like doing these tables because it just organizes my, approach and gets me doing one little step at a time, which seems to be helpful. All right, so that gets you got M, you can get C, you can get I. So now you can find the bend, you found I. So now you can get the bending stress, okay? We all right with that? Okay, so we just need to, I'll tell you what, let's find one more thing while we got time. Let's go ahead and get into the shear stuff. So let's find Q. Find Q for this one. Now what we're finding Q for is 0.1 down there. So let's go ahead and find Q here. So we're looking at 0.1. Draw a line through 1. I usually take the smaller piece and say, okay, I'm looking at that thing shearing off. Okay? So what you'll see on your formula sheet is Q is A times D, the area times the offset distance. So step 1 is find the area that would shear off. Step 2 is find the distance from the neutral axis to the centroid of the area that would shear off. So that's Q. I always like my pictures. It's the neutral axis. Getting 0.003168. Okay. That's the area that would shear off from the times the distance from the centroid, or excuse me, from the neutral axis to the centroid of the area. So what you want to get is this distance right there to that point.
And that's our difference.
Yes. A is the area that would shear off. D is that distance. And I would suggest on this stuff, I know it's the end of the term and we start getting a little tired and all that, but just go through this stuff and sigma is MC over I. M is off the moment diagram. C is the distance from the neutral axis to the either edge of the beam. I is the moment of inertia. Shear is V off the shear diagram. Q, which is what I'm showing here, over I, which is just the moment of inertia, and T, the thickness of the beam. Just get that stuff figured out, and find each one of those things and plug them into the formula. I have had some issues with this in the final in the past, but if you figure out what all those things are and what they mean, just find each one individually and then plug it in, Okay? So there's Q. Okay, so what we're doing there, we're going from the neutral axis, which is right there, and we're going down to that centroid. All right, so the centroid is half of the 4 centimeters, which is 2 centimeters. It's 0.02, and the neutral axis is 0.108 high, so the difference is 0.088. And it's actually a negative here, not that it's a big deal, but usually you don't really use signs on this stuff too much when you're doing shear. Okay, and you multiply that by the area that would shear off, and that's where the 0.0003168 meters cubed comes from. Y'all okay with this bit? Okay, good, good, good to go. Okay, good. All right, so now you pretty much got all the pieces, and there's just the two formulas. There's the bending stress formula, sigma is mc over I, and the shear stress formula, tau is vq over it. So we're about out of time. We'll finish these up tomorrow. Why don't I just give you the answers? So just, if you want to be looking at it. And, I'm doing this, frankly, because this is a very good review for the final. I mean, drawing up a shear moment diagram, finding these stresses. That's something I'll have you do on the final. So that's why I want you to be able to do this stuff. So what I got for tau, and that's it. Is that B1? Is that correct? B1? Yeah, okay. And I got 1.28 megapascals. And we'll look at these tomorrow, but see if you can get these figured out by tomorrow. And then sigma, compression, and this is max, okay? And then we got sigma T max. They're slightly different. The compression, I got 163 megapascals. And the tension, I got 157 megapascals, okay? All right, so we'll just finish this up tomorrow. We'll go over.
Thanks.